K2-18b, the James Webb Space Telescope, and the early universe, a cosmic journey into habitability and origins. To astronomers, such a location is like striking cosmic gold. If a planet sits too close to its star, its oceans boil away, too far and water freezes solid. But K2-18b orbits within that sweet spot, and that immediately put it on the radar of exoplanet hunters searching for potentially habitable worlds. This super-Earth, about 8.6 times the mass of our own planet, occupies a unique category of exoplanets that fall between the size of Earth and Neptune. This planetary class, sometimes called sub-Neptunes or mini-Neptunes, is conspicuously absent from our own solar system. That uniqueness alone makes K2-18b an object of considerable interest. Why does our solar system lack such a planet when they appear to be among the most common planet types in the galaxy? Could it be coincidence? Or did our solar system evolve in a way that specifically prevented such worlds from forming? Studying planets like K2-18b may help answer that question. But what truly sets K2-18b apart is the composition of its atmosphere. Using its unmatched infrared sensitivity, the James Webb Space Telescope, JWST, has identified the presence of carbon compounds, specifically methane and carbon dioxide, within K2-18b's atmospheric envelope. These are not trivial detections. Methane and carbon dioxide are both considered key chemical indicators when scientists assess whether a planet could support life or sustain the kind of chemistry associated with life's building blocks. This points to the possibility of a hydrogen-rich atmosphere overlaying a planet covered in oceans, a configuration that could, at least in theory, support life, even if not directly biological life as we know it. Such an environment might nurture prebiotic chemistry, the kind of molecular experimentation that could eventually give rise to living systems. This discovery builds upon earlier data obtained by NASA's Hubble Space Telescope, which first offered a glimpse into K2-18b's atmosphere and opened the door for more in-depth analysis. Hubble's detection hinted at water vapor and carbon-based molecules, sparking debates and enthusiasm. However, while Hubble laid the groundwork, it is Webb's cutting-edge spectrographic capabilities that have delivered the most detailed atmospheric reading of a habitable zone exoplanet to date. One of the most intriguing aspects of the new findings is the potential presence of dimethyl sulfide, DMS, a molecule that on Earth is predominantly produced by marine organisms, particularly phytoplankton. This is a stunning prospect. DMS is considered a biosignature gas, meaning that on Earth nearly all of it comes from life. Although evidence of DMS in K2-18b's atmosphere remains tentative and unconfirmed, the very suggestion of a biosignature gas being detectable from such an incredible distance has electrified researchers across disciplines. If validated, it would mark an unprecedented leap forward in our search for extraterrestrial life. Yet scientists are understandably cautious. A researcher from a University of Cambridge pointed out that while the presence of carbon molecules and location within the habitable zone are promising indicators, they are not definitive proof of life. The planet's structure, likely featuring a high-pressure mantle of ice similar to Neptune, covered by a thin hydrogen-rich atmosphere, could still be inhospitable despite the potential presence of oceans. These extreme conditions might render any liquid water either inaccessible or unsuitable for life as we know it. Nevertheless, what remains undeniable is the technological triumph of detecting such complex atmospheric signatures. The method used hinges on a phenomenon known as planetary transit. This occurs when a planet crosses in front of its host star from our viewpoint on Earth, causing a slight dip in the star's observed brightness. During these transits, some of the starlight passes through the exoplanet's atmosphere before reaching us. That starlight is imprinted with chemical fingerprints because different molecules absorb specific wavelengths of light. Webb's instruments can capture and analyze these subtle changes with remarkable precision, offering insights that were previously impossible to obtain. Future observations using Webb's mid-infrared spectrograph, MIRI, are expected to further refine our understanding of K2-18b's atmosphere and climate and possibly confirm the presence of molecules like dimethyl sulfide. The ultimate objective of these ongoing studies is nothing short of revolutionary: to determine whether habitable exoplanets exist, and if so, whether they show signs of life. But the telescope's revelations are not limited to nearby exoplanets. In another groundbreaking observation, astronomers using Webb detected complex organic molecules, specifically aromatic hydrocarbons, in a distant galaxy formed when the universe was only about 10% of its current age. These molecules, which on Earth are associated with petroleum, coal deposits, and pollution like smog, were previously thought to be far too complex to exist so early in the universe's history. Their detection fundamentally challenges prevailing cosmological models by suggesting that organic chemical complexity arose much earlier than we once believed. The molecules discovered are not simple compounds like water or carbon dioxide, but instead large molecular structures composed of dozens or even hundreds of atoms. These are among the most complex organic molecules ever observed in space, and their presence in such a young galaxy raises profound questions about the early universe's capacity to foster the building blocks of life. The light carrying the signature of these molecules began its journey less than 1.5 billion years after the Big Bang, a blink of an eye in cosmic terms. Considering the universe is estimated to be around 13.8 billion years old, the fact that astronomers can now study this ancient light in such detail is a testament to Webb's extraordinary sensitivity and technological sophistication. Prior attempts to detect organic molecules in ancient galaxies could only establish their general presence. But the Webb telescope allows scientists to map where these molecules are located within their galactic environments. One particularly puzzling discovery is the non-uniform distribution of these molecules in a galaxy known as SPT 0418-47. The irregularity adds another layer of complexity, hinting at processes we do not yet fully understand. Even more astonishing is that this early galaxy appears to be as massive as our Milky Way and already harbors stars that have produced as much carbon and oxygen as those in our galaxy today, despite being only a tenth of its age. Such findings suggest that galaxy formation and chemical evolution may have proceeded far more rapidly in the early universe than previously thought. Taken together, the discoveries of carbon-based molecules on K2-18b and complex hydrocarbons in a primordial galaxy offer dual perspectives on life's potential origins. One is grounded in the search for habitable planets in our cosmic neighborhood. The other looks deep into the past to understand how the essential ingredients for life emerged in the early universe. These breakthroughs not only enhance our knowledge but also provoke new questions about how common life-bearing worlds might be and how quickly the universe became chemically enriched. The James Webb Space Telescope has fundamentally reshaped how we explore space. With each observation it sends back to Earth, it challenges scientists to reconsider long-held assumptions and entertains the possibility that life, or at least the ingredients for life, may be more widespread than previously imagined. The ability to detect subtle molecular signals from planets dozens or hundreds of light-years away and from galaxies that existed nearly 13 billion years ago reflects an extraordinary leap in our technological capabilities. These advances are more than just academic achievements. They represent humanity's drive to understand the cosmos at its most fundamental levels. The discovery of carbon compounds in the atmosphere of K2-18b may not yet prove the existence of life, but it brings us closer than ever before to answering that age-old question: are we alone? Meanwhile, the detection of complex organic molecules in one of the earliest galaxies adds a new dimension to our understanding of cosmic history, suggesting that the chemistry of life was already underway when the universe was still in its infancy. As astronomers prepare for more in-depth studies and await further data from Webb's mid-infrared instruments, anticipation builds. The coming years may well see the telescope unveil more astonishing secrets that will continue to redefine not only our knowledge of the universe but also our understanding of life's potential throughout the cosmos. With each new milestone, the James Webb Space